Hi everyone, and welcome to week 2 of Scripting for Forensics. This week I'm going to introduce the topic of cryptographic hashing, and we're going to use that in a couple of scripts. So I want to actually kind of introduce the general concept. You may already be familiar with this concept, however, I want to make sure that we kind of provide a solid foundation as it refers to Python and scripting in that environment. So let's start by talking about what cryptographic hashing is. In other words, we want to use this typically to verify evidence with these digital hashes that are generated. So the key concepts that I want to cover today is what is cryptographic hashing, what is a message digest that is generated by the cryptographic hashing function, and how are hash values, the message digests that are generated, utilized in forensics. We're going to just cover those three quick concepts as we kind of walk through this briefing. So cryptographic one-way hashing has always been an integral part of digital investigations, incident response, and even e-discovery. So the concept behind this is that I can take any piece of data, whether it was a password, whether it was a string, whether it was a file, whether it was a image of a hard drive or an image of a memory stick, an image of a phone, whatever it happened to be, and I can take that data and I can run it through a hashing algorithm. There are many of those available. That hashing algorithm will produce a message digest. The message digest that it produces will be different depending upon what algorithm I'm using. So if I'm using an MD5 hashing algorithm, it will produce a 128-bit message digest. If I'm using SHA-256, it's going to produce a 256-bit message digest. And if I'm using SHA-512, obviously it'll produce a 512-bit message digest. So the one-wayness of this, and the reason we talk about this in one way, is we can only go in this direction. It's infeasible for you to take a message digest and produce the original value. The reason I say infeasible instead of impossible here is there have been some attacks based on message digest and on hashing algorithms that can overcome this. But understand, those are from very laboratory environments, very specific attacks on those that are really not an issue for us in forensics at all, regardless of what anybody says. It's very, very difficult to accomplish, and there are other checks and balances that we can put in place. So understand, the concept is I'm taking in some plain text data, it can be any kind of binary or text value, I'm going to perform an algorithm on it, and I'm going to produce a message digest, and I have that. And I can use that in several different ways within forensics and digital investigations. So cryptographic hashing, the strong hashing methods contain 4 common traits that are important to understand. First, the hash function itself is easy to calculate and generates a strong message digest. And as I mentioned before, they vary in length. So as you get larger message digest, the strength of the hash value continues to increase. The reason is just the fact that the longer the message digest, the more possible variants I have in order to be able to process those. Possessing the message digest alone doesn't provide any clues to the original message, file, or image that was hashed. It's infeasible to change the contents of the message or file without changing the associated message digest. So if I attempt to manipulate the file, the image, whatever, it's going to change the message digest, even if I change just a single bit. It's also infeasible to find 2 messages or files that differ in content but produce the same message digest. At NIST, they run something called the National Software Reference Library, and they collect hashes from virtually every executable program that has been created in the last 20 years. And during that process, they have generated hundreds of millions of hashes, and none of them have collided in that manner. Cryptographic hashing, when we're looking at it from a Python perspective, the Python standard library offers a broad set of hashing methods. They include RSA's MD5, which was one of the original algorithms that is still used very often within forensics. And then the National Institute of Standards and Technology, NIST, have produced several additional standard algorithms, SHA-1 through SHA-512, that are available. All of these are built into a library that is part of the Python standard library. Therefore, it operates across all of the platforms, whether it's Windows, Mac, or Linux. These methods are very fast, as they are written in a lower level language, like many of the core libraries are, so they're just as quick as if I was writing this in assembly or C in order to be able to operate. So how do we do this within Python? Well, the first thing we have to do is we have to import that library. So we use a simple import statement that says I'm going to import the standard library. Then I have to basically create an object. So just like we created a string, it looks a little more complicated. I'm not saying my string and giving it a string. I'm actually calling a function to create the object. So I'm using the hash library, and I've decided I want to create a hashing object of the type SHA-256. Now that I've created the object, I can use it to update its contents with data. And I can use this update function multiple times. But in this simple example, I'm going to basically use data to hash, just a simple string that I want to actually create the digest for. Then I can again use the hash object and the function hexDigest in order to actually recover what is the current digest that I was talking about more. We talk about these typically as the hash value, but it's actually a message digest, and that's what that message digest would look like for the data to hash string. So that's how you actually do this, and you can experiment with this on your own. Within the Wing IDE shell, for example, you can type this in and you should get the same results. So how are they used in digital forensics? Well, they're used to generation of digests for image media. So whether it was a thumb drive, whether it's a memory stick, whether it's a hard drive or a phone, whatever we're imaging, we use the digest to basically mark that associated with that particular image that was generated. We can generate digests for specific known or bad files. And then we can search for those known or bad files using the hash value. We don't have to actually look at all of the data. We can hash the file and compare it to a list of hashes so we know what it might be. We also use them in something called rainbow tables that you might want to look up. And this is for the conversion of, let's say, an intercepted hash value to a brute force set of passwords. So we can then basically convert a hash value that was intercepted, let's say when somebody was actually trying to log into a system, we can use that to convert it back to the original hash value, original password value, so that you can actually use it from that perspective. So that's kind of the end of the introduction. Your immediate actions for this week are to read Chapter 3 in the textbook. It kind of covers digital hashing in a little bit more detail. Watch the additional videos that I've provided for you to walk you through some fundamentals in Python, as well as getting into hashing in a little bit more detail. Participate in the Week 2 discussion. Complete the Week 2 quiz. A word of warning, before you take the quiz, make sure you watch all the videos, you read the chapter, you experiment with the sample code that I've provided so that you're prepared to take the quiz. And then complete the Week 2 assignment, which is pretty straightforward. I just want to make sure that you're able to execute the pfish.py script. So the proof of that is just executing that script and taking a screenshot. But review that assignment as well. And I look forward to communicating with you online this week. Have a great week, and review the additional videos that are available for you.